Hello everyone, welcome to the 8th video in this series for Simulink model for electrical circuits. In this video, we are going to implement a three-phase voltage source inverter, that is VSI circuit. So a VSI circuit is basically used to convert a constant DC voltage to a three-phase AC voltage with a control magnitude and frequency. That is VSI circuit. It can convert the DC voltage into a three-phase voltage source of a controlled or of a required magnitude and frequency. So for designing a VSI circuit, Uh, generally, we use switches, that is electronic switches, such as MOSFET. Okay, so in this video, we'll be using MOSFET to implement this VSI inverter circuit. So let's have a look at the question. So basically, we have to design a three-phase conduction mode VSI inverter with a DC input of 450 volt and the following specification. So these are the specification which we have to use to implement this three-phase VSI circuit. And we also have to investigate how the conduction mode affects harmonics injected in the supply system and the quality of the output signal. Okay, so we have to basically analyze how the output signal or the quality of output signal is affected by the conduction mode. Now the AC output voltage which we need to produce is 315 volt. The frequency should be 50 hertz and the load resistance should be 10 ohms. Okay, so now let us go to Simulink and try to implement this circuit. Now to implement this three-phase VSI inverter circuit, the first thing that we'll need is a DC voltage source. Okay, so let's search for a DC voltage source. Okay, so we are going to use this one. Okay, now the DC supply voltage should be 450 volts. Okay, so let's change this parameter. Next, we need a power transistor. So let's search for MOSFET. Okay, so let us go down and this one. So let's add it in the main screen. Now I'll have to rotate it and flip it as well. Okay, so what I'm going to do is I can select this component and press Ctrl R. To align it properly or to make the connections properly, I'll have to flip it as well. So I'll right click, go into format and flip block left to right. Okay, so the gate terminal is on the left hand side. Okay, the next thing we'll need is a pulse generator. to trigger this MOSFET. Okay, so let's add this pulse generator. Now the parameters of this pulse generator, I'll have to uh, change the parameters now. So the amplitude should be 5. The period, it should be 1 divided by 50. So 50 Hertz is my frequency. Pulse width should be, we can use a variable, let's say CA. So CA is your commutation angle. Commutation angle. Okay. So I'm abbreviating it and using a variable CA. So CA divided by 360. I'll have to use the brackets, multiplied by 100 to convert from an angle to time in seconds. Of course, it will show an error because I'll have to define the value, the numerical value for this variable. Okay. Now phase delay. So each trigger will be delayed by 60 degree. Right. So we will have to use different values for the phase delay. So for the time being, let us keep it as 0 degree. Okay. I can apply it and okay. Let's turn on the block names. Okay, and connect it to the MOSFET like that at the gate terminal. Right. Now let us copy this and paste 6 of them. So there should be total 6 of these MOSFET along with the pulse generator. And now we need to name the MOSFETs. So I'm going to name it as T1, T2, T3 and so on. Okay. So the first one, I'm going to name it as T1. Now the T2, it will be this one. Right? And then T3 should be this one. Right? So we have T1, T2, T3. Okay. T3, then T4 will be this one. T4 and T5 will be the last one on the top. Okay, T5, and obviously the last remaining MOSFET, it will be T6. So numbering it or labeling it is quite important. So I have not labeled it in a sequence. Okay, so please keep a note of that. Now after labeling it, let us now change the phase delay or the time delay in all the pulse generator for the different MOSFET. So T1, the phase delay will be uh, 0. Okay, so I can leave it as it is. Now T2, the phase delay should be 60. There should be a difference of 60 degree. 60 divided by 360, and I have to convert it into time. That is, multiply it with the frequency. That is 20 e to the power minus 3. Okay, I'll copy this and it will help me to change the other easily. Now T3, it will have a phase delay of another 60 degree difference. Okay, so this time it should be 60 plus 60, that is 120. So for T3, the phase delay will be 120 divided by 360 multiplied by 20 e to the power minus 3. Similarly, T4, it will be 180. Okay, so it will be 180 divided by 360 multiplied by 20 e to the power minus 3. And T5, it will be further 60 degree delay. So T5, it will be 240. Okay, and T6, so T6 will be 300. Okay, so it will be 300 divided by 360 multiplied by 20 e to the power minus 3. Yeah. Now we will make the connections for the MOSFET. Okay, so to connect the MOSFET, what I will do is, first of all, I'll connect the source to the drain. So the source terminal of the top MOSFET to the drain terminal for the bottom. Okay, and then I will connect the drain terminals for all the three top MOSFET, or all the three MOSFETs in the top together, and the source terminals, again I'll connect them together like that. Okay, next we will have to add a three-phase RLC branch. Okay, so let's search for three-phase series RLC. Let's search for series RLC. Okay, so we are going to use this three-phase series RLC branch. Okay, so let's drop it here. Now the value for this resistor is, or the load resistor is 10 ohms. Okay, so I have changed the branch type to resistor only and 10 ohms. Okay. Now the capital A, B, C, I'll connect it to the three lines here. Okay, so A, B, and C, like that. And the small A, B, C, I'm going to connect them together and connect it to ground. Okay, so let's search and add the ground block. And connect all the three uh, terminals together and connect them to ground. Okay. Now similarly, this is my DC voltage source. So I have to connect it to the VSI inverter circuit. So I can connect it there like that. Okay. And I have to change the parameter to, I've already changed the parameter to 450 volts. Okay. Next, to measure the line current and the voltage, uh, we have to add the current measurement block. So let us search for this current measurement block. Okay. And also we will need a scope. Okay. So let's search for scope and add it. Right. So this current measurement, I can connect it here. Okay. For just one of the lines, I can measure the current. Okay. Okay. There we go. So I've added the current measurement and I'll use the scope and also we will need to measure the voltage. Okay, so we will need a voltage measurement block. Okay, so I have to measure the voltage, let's say between A and B. Okay, something like that. Okay, now to connect the scope, so we will need 5 inputs. Okay, so let us change the number of inputs to 5. Okay, and if we click the tab on logging and log data to workspace. Okay, just enable this option. So it's going to uh, export all the data to MATLAB in a file. Okay. Next, if we go to display, let's label all the display. So the active display 1, it will be titled as voltage. Okay. And let's change the layout first to 5. So I can select it something like this. Okay. So if I go to active display, the first active display should be titled voltage. The second one, I can title it as current, and the third one I will give the title as T1. The fourth display I will give the title as T2. Okay. And the fifth active display I will give the title as T3. Okay. Now let us connect the scope. Okay. So the first terminal, it will be connected to the voltage measurement. Okay. The second terminal, I'll connect it to the current measurement. Now the third terminal, I'm going to connect it to T1. Okay. So to avoid complication, I will use the go to block and from block. Okay. So go to, I will connect it to T1. Okay. Let's rotate it. And connect it to this, the gate or the pulse generator connected to T1. Now next let us add the from block. So go to A, and this is from A. So this block, it will send the signal to from block A. Okay. Now the fourth terminal I will connect to T2, this one. Okay, so again I will use the go to block and connect it to T2 like that. Okay, and I will change the name of the variable to B, and I will connect it here and change it to B. Okay, and the last terminal, the fifth terminal, I will connect to T3 and change the variable to C. Okay. from block and change the variable for the from block to C. Okay, so A, B, C. So T1 and B is T2, C is T3. Okay, now let's add the Power GUI. Next, we need to do some more measurement. Okay, so first we'll need to measure the RMS values. Okay, the RMS voltage. So let's search for true RMS and connect it to the voltage. Then we will need a display to display the number. So let's go down and select this one. Okay, now obviously we have to change the fundamental frequency for the RMS block to 50. Okay, um, next we will need to measure the total harmonic distortion. So let's search for the THD block. Okay, and let's say add it here. Okay, now for the THD, let's again change the fundamental frequency to 50 Hertz and the sample time to 5e minus 5. Okay, now I will need a gain block. So let's add it here and let's change the gain to 100 to calculate the percentage. Okay, and so this THD block will be connected to the current. Okay, and we will need a display. So this is my THD in percentage. Okay, and this is my RMS voltage. Okay, now uh, let's change the stop time to 0.1 seconds. Okay, now we have used a variable CA, okay, in all the pulse generators. So I'll have to go to MATLAB and add this variable or assign the value to this variable, that is CA. Let's take 120 degree. So commutation angle we are testing for 120 degree. Okay. Now if we go back to our block uh, and run the circuit. So for 120 degree uh, commutation angle, the RMS value for voltage, it is 315, and the total harmonic distortion is 31.17. Now let us look at the waveforms. Okay, so the voltage waveform or the output voltage for one of the phase. Okay, so we have connected a voltage measurement to one of the phases. Okay, it is kind of, you are getting alternating voltage but with some harmonics, or it's a bit noisy. Okay, and the current waveform also, if you see, you're getting around 20. Okay, uh, 20 amperes, and it is also alternating. Now the delay between the three uh, pulse generator or square waves which we have connected to trigger the MOSFETs, the phase delay between them is uh, 60. So you can verify the effect of changing the commutation angle, right? So we have currently simulated the circuit for 120 degree. You can do it for 150, 180 degree commutation angles as well. Okay. Another thing which we have done in the scope block is that we have logged the data. So we can use that data to do fast Fourier transform analysis. Now to do the FFT analysis, we can go into the scope and go into the configuration properties and logging. So we have already checked the log data to workspace. Also check the limit data point to last this 5000 is okay. And save format, you have to uh, change it to structure with time. Variable name, you can put in any variable name. For the time being it is scope data, so I've left it as it is. Okay. Now another thing which you should do is check if in the modeling tab and in the model settings, if this single simulation output, it is checked or not. If it is checked, uncheck it. Okay, don't select this option, single simulation output. This block should be unchecked, otherwise it will log the data but compile it together into a single simulation output. So when we are doing the FFT analysis, uh, you won't be able to see the different signals. Okay. Now, once we have changed all those settings, we can go into continuous or this Power GUI and then go into tools and select FFT analysis. So in the FFT analysis, you can see it has already selected the scope data. Okay. Now in the MATLAB, in the workspace, if I go, I have my scope data. Okay. So it has saved uh, the output of the Simulink as scope data. Right. So I have all my uh, inputs. They have been logged. Now in the FFT analysis, let's change the signal to input 2, which is my current. Okay, and then start time is okay. Change the fundamental frequency to 50 Hertz, and then click the compute FFT. So this is the total harmonic distortion at 50 Hertz, right? So the magnitude is coming out to be around 18.7, and the total harmonic distortion is 57.76%. Now the other thing which we can do is we can change the commutation angle. So we have already verified the circuit for 120-degree commutation angle. The RMS voltage, it was 315, and the total harmonic distortion, it was 13.17. Now if we change the commutation angle to, let's say, 150-degree and run the simulation again, what we can see is the waveform, or the alternating voltage and current, they have become slightly smoother, right? And the total harmonic distortion has also reduced. Okay, it has reduced to 16.8%. The VRMS is 340 now. Okay, and if we update it and compute the FFT analysis, we can see that at 50 Hertz the magnitude is 22.13, and obviously the waveform, or the current waveform, is much smoother. Okay, let's again try to increase the commutation angle, and let's make it 180. Okay, and then again let's run the circuit. So by increasing the commutation angle to 180, we can see it's not very smooth, and the total harmonic distortion has also increased. Now coming back to the slides, for 120-degree commutation angle, the measured load voltage, it was 315 volts. Okay, and if we do the calculation using these formula, the output voltage, it was coming out to be 319. Okay, so this is the circuit, and these are the waveforms which we have observed. Now the commutation angle for 120 degree, if we convert it into time, it comes out to be 6.68 milliseconds. So we can also measure it from Simulink. Uh, Basically, this if you measure the the width of each of these pulses, uh, that will come out to be 6.98 approximately. So quite close enough. And the time between switching is half of this pulse width, right, which is 3.4 or 3.39 milliseconds, which is 60 degree. Now we have also tried for different commutation angles, uh, and 150, the commutation angle of 150 was giving us the best results. Okay. Uh, Another thing which we can include in the circuit to further improve the waveform or to smooth the output, make the output smoother, is add a inductance. So we can calculate the suitable inductance using these two formulas. So basically inductive reactance is 2 pi FL, and from that if we calculate the value of inductance L, uh, we get this as 0.64 Henry. Okay, so let's try and include this inductor as well. Change the commutation angle to 150, and so we are getting much smoother waveform. And the load, so the load, I'm going to change it to RL, and the inductance that we can include is 0.64 Henry. Okay, so if we look at the current waveform, you can see how smooth it has become. Okay, and from the circuit also, if you check the total harmonic distortion, it is 4.64. Okay, the VRMS is slightly higher, 367.4. Okay, and if we do the FFT analysis for the second input, which is current, and the total harmonic distortion according to the FFT analysis is also reduced. Okay, uh, right. So these were all the things that I wanted to discuss with you in this video. So basically we have learned to design a VSI circuit and analyze the waveform for the circuit. Okay, and also do the FFT analysis. So this is it for this video. Thank you for watching this video and hope to see you in the next one.